Hello, everyone. Welcome back to the NET Physics series. And today we'll be starting chapter number 8 for NET Physics, which is of waves. Now, a wave is really produced, you could say, due to the disturbance that you can create in any medium. So, for example, if you consider you have a sea, right, and I throw a pebble of rock into the sea, it would, you can imagine the situation, it would really create waves around it, which would propagate into further into the sea, right? Now, these waves that you see over here, they will transport energies. So waves they really transport energies, but they will not really transport or move any matter for that matter, right? Now, you can have waves of different types. You can have waves, for example, we have water waves, we have waves on, you could say, a string. You vibrate a string, you could see waves. Now these type of waves are visible waves. You can also have invisible type of waves, which are, if you think about it, sound waves. Sound is really something waving, and that is invisible. Also, you have waves that are produced due to matter, and we learn about this in detail as well. We also have electromagnetic waves, now which include light waves, radio waves, x-rays, and so on. So these type of waves, they are invisible to the naked eye. Now, string waves are really mechanical waves, and when we are working with mechanical waves, we are really dealing with the cooperative motion of the collection of particles that are from the wave. And the mechanical waves, they require a medium to propagate further into space. However, the case of waves which are electromagnetic waves, these are the waves you can for example say radio waves, heat waves, light waves, x-rays, and so on. These type of waves, they do not require any medium to propagate in space. And this is one of the reasons that if you are on earth and you can see the light from the sun, you're standing on the earth, you can clearly see the light that is coming from the sun to earth. However, because there are lots of reactions happening on the sun, nuclear fusion which happens on the sun, where two or more, you could say, nuclei, they combine together, and so that is a very violent reaction, and it would produce lots of sounds if there was any medium and near the sun. But there is this whole space between the earth and the sun is really empty. There is no medium for that sound wave to propagate, and so you cannot hear sound. However, you can see the light that is emitted from the sun to the earth. And that's simply because sound waves cannot propagate to the earth because there is no medium in between these two. However, light waves can propagate as they do not require any medium to move through space. We can further classify waves into two types, as traveling waves and periodic waves. Now, a traveling wave is really a type of wave which will propagate all of its pulses in space along a specific direction. So you could imagine, for example, a string which is tied at these two ends and you pluck it from anywhere, or you can just swing it, you could say, and it would produce a wave, and this wave would be traveling really in this direction, right? So it's propagating all of its pulses in a specific direction along space, which may be in this direction. Another example for traveling waves is the one that I gave initially as this a rock being thrown into a pond or a sea, which would really produce waves on this water surface, right? Then we have periodic waves, and periodic waves are those which are really represented in a particular regular interval of time. And so you can draw something like this, which might look similar to traveling waves, but it's periodic. So this is one wave, and then whatever happens after this, it's just this pattern being repeated, right? So it's being repeated after some interval of time. If I have time on this axis, and let's say that you have position on this axis. Now these periodic waves, we can classify periodic waves in to two types as well. So we have transverse waves and we have longitudinal waves. Now in the case of a transverse periodic wave, the displacement of the medium is really perpendicular to the direction of the motion or propagation of this wave. So it looks something which I really actually drew over here. So let me just do this one more time and I'll show you that this type of a wave is really a transverse wave if the direction of propagation is this way. So this is where it's the velocity vector really points, so it's moving in this direction, while the displacement of the wave is perpendicular. So it's, you can see over here, it is perpendicular to the direction of velocity, right? And so these type of waves are really transverse waves, right? And these transverse waves, they can some of the examples, or you can say that these type of waves occur on a string or on the surface of water, or for that matter any liquid, and even throughout an entire solid as well. Now it is important to note that these type of waves, transverse waves, they cannot propagate in gases. They cannot propagate in gases, or we could say in fluids really. So fluids is just gases or a liquid, and the reason for that is because in a fluid there is really no way for driving motion to be perpendicular to the propagation of a wave, right? Now the other thing we have is the longitudinal wave, and in longitudinal waves the displacement of the medium is actually parallel to the direction of propagation. So you could think of a slinky, which is just a spring, and it's like this, and the waves that are being produced in this slinky when you expand or contract it, or when you you can say that you just direction it downwards, so the gravity acts on it, and you know it would be something like this, and then it would basically expand or contract because of the weight of the spring as well. So in this case the displacement and the you can see that it is when you this slinky will expand, its displacement will be either in this way, or its displacement will be either in this way, which is parallel to the direction of propagation of the wave in this slinky, right? In this case, the displacement is either in this way or it's either in this way, and it's still parallel to this slinky, which means that the wave that will propagate in this slinky would really be parallel to the direction of the displacement. Now, one of the examples for these longitudinal waves are sound waves in air, right? So in this case, the velocity of propagation of the waves is in this direction, while the displacement is also in that direction. So this is really either parallel or anti-parallel to the slinky. Now, as we discussed, that in transverse waves, the they'll they'll just very quickly, you could say, they'll just die out in fluid case, and it's usually the case that the in fluids there is, you will never really see a transverse wave for a case of a fluid. Note that the waves that we're talking about, all of these waves, they carry some energy with them, and when they propagate through a medium, what they're really doing is they're transporting their energy and momentum as well into that medium. Now let's quickly discuss some of the properties really of a transverse periodic wave. So for example, let me just draw it once more, and if this is the time and this is the displacement, let's call it x, and you have, for a transverse wave, you have something like this. Now in a time interval which is really equal to the time period, which would mean from this point to this point, the particle will travel in this wave, and the distance that it travels is really known as the wave length of the particle, or the wave, right? Now again, it is really it is represented with a symbol lambda, and again it is defined as the distance that my particle will travel in time, which is really equal to the time period of this oscillation. So any distance that is covered within a time period is defined as the wavelength of this wave. Now, all of the waves follow a relation which is that the velocity of the waves is given by the product of frequency of the wave and the wavelength, which is really wavelength divided by t, right? Because frequency is 1 by t. So the particles that are in a wave, they are separated by a distance which would be really an integral multiple of this lambda. So you can say that we have n lambda, where n is just an integer, and n lambda are in phase motion. The particles n lambda are in phase motion with each other, right? So they are in phase when they are moving on this wave. So this is the case when we have in phase, while you could also consider when you could say that the particles are separated by some odd multiple of lambda, right? So let me just say that this is an even it's really just any integral multiple of lambda. But if the particles are separated by odd multiple of lambda, then we have a case where you can write it as n plus 1 by 2, which would make any uh, uh, multiple as an odd multiple of lambda. Now these are those type of particles which are out of phase. So that's how you really define in phase and out phase particles. Moving on, we can now talk about sound waves. Now, really, any body that vibrates will give rise to sound waves. Any vibrating body will give rise to sound waves, and they are typically of the wavelength of around 1 meters. Now, there are some things that you need uh, as an essentials for detecting sound waves. So these essentials are: number one, we must have obviously we must have a vibrating body, right? As we just discussed, and this vibrating body will be producing the sound waves. Secondly, we must have a medium, and this medium is there really to provide the propagation of these sound waves. And finally, we should have a listener, or for that matter any detector that is really possible for detecting sound waves. It does not always have to be a conscious being, right? So it could be an ear or just any detector for that matter. So this would be there for detecting the sound wave. Now suppose that I have this reference line, and at this line we have 1 atm, which is just the atmospheric pressure at this line, and then you have you can say a sound wave that is traveling along, you can say that this from this reference point. Here you could have two cases where you see that when the wave is above the atmospheric pressure, at this point there is some increased pressure, and when the wave is below this reference line, with below 1 atm, at this point there is some decrease in pressure. So that's what these really mean, right? What that now means is that sound waves are really a type of pressure waves where we can have compressions when we have increased pressure, and we could also have something that is called rarefactions where the particles are displaced further, and we'll look at that. But what really it means for a wave to be a pressure wave is just that this, for example, the sound wave, it is consisting of patterns of high or increased pressure and patterns where we have decreased pressure. And these type of waves are really also called a pressure wave. And it really looks, if I try to draw it, it would look something like this. If you have a medium, and here we have these regions where you have particles which are very closer to each other, and like this, and then here we have some gap between the particles, and then again you have a region where you have particles that are very closer to each other, and then again you have a region where they're, well, not so close, they're really displaced, and then again you have this region where they're pretty close to each other, and then again they're just displaced like this. And then you can have that on and on, but we'll just stop. Of course we have to stop somewhere, right? And so these are the regions for compression. This is compression, we denote that with C. This is rarefaction, where the particles are really displaced further apart. And then again you have compression, rarefaction, compression, rarefaction, and so on, right? So you could have these regions. Now on a graph, this thing really looks like a wave that is really oscillating. If this vertical axis were pressure, and here you have time, then this compression region looks like where we have very high pressure. Then we have rarefaction, where the pressure is really low, and then you have again compression, so it's very high, then rarefaction, and then compression, and so on, right? So this graph is very weird shape because of my drawing, but you get the point, right? So this region corresponds to compression, whereas this region corresponds to rarefaction, right? And so because there is a transition between the two, it must cross the zero pressure as well. Of course, this diagram may be leading to wrong information as well if you're not careful, because it might seem that this wave is like a transverse wave, but it really is not. You cannot just conclude that sound wave is a transverse wave where you have crests and troughs, right? Because sound waves are traveling through air and they are longitudinal indeed, but they just have these regions of compression and rarefactions, which we represented on a graphical thing like this using a sine function, really. So being longitudinal, sound waves, they have three dimensions of propagation in space, right? So they they exist. This slinky, if you consider this example of slinky, it's a three-dimensional object, but the direction of the motion of waves and the displacement of those waves both are parallel to each other. Now again, we have really discussed these regions of compression and rarefactions. Just remember that compression is a region where you have particles that are very close to each other, or you can say it's a region where we have crowded particles, while and that region, those number of particles are maximum in that region, while we have another one which is the rarefaction, where the particles are further apart from each other, and you can also say that the crowding of the particles is minimum at this point in rarefaction regions. Now, sound waves are really capable of producing different phenomena, which are reflection can be produced from sound waves, and you could also have refraction of sound waves. Diffraction is also possible, right? Diffraction is also possible. We can have sound waves which are interfering with each other, so interference is also possible. What is not possible, however, is polarization is not possible. So you cannot really polarize your waves, sound waves, in a particular direction, right? And the reason for that is simply because these waves are not traveling orthogonal to the direction of motion. The displacement, I mean, of the waves is not really perpendicular to the direction of motion, as they are as they're not transverse, right? So they're longitudinal waves. Moving on, we can discuss the case of intensity of sound waves. Now, the intensity of sound waves is really defined as the power of this sound per unit area. Now, this intensity of the sound is really measured in the air at the listener's location. And so the units for intensity of sound are really watts per meter squared. However, one of the more common approach to the measurement of this sound intensity is known as the decibel scale, right? So it's the decibel scale, and this scale is defined as you can write your intensity in decibel scale, where you denote it with dB. So this is the intensity in decibel scale is really 10 times log to the base 10 of the ratio of intensity to some initial value of intensity. So, for example, you could consider that you have a loud speaker over here, and the speaker is really emitting sound waves. Then the intensity of the sound waves is really defined as the sound waves that pass through this. You could say this is some area, right? This is some area, and the sound waves that pass through this area. Uh, So it is really the power that is carried by these sound waves per unit area, and these sound waves are really perpendicular to the direction of this area, right? Moving on to the velocity of sound waves in air, you can really determine speeds of any mechanical wave by using an expression for velocity, which is v is equal to square root of e over rho. Now note that e over here is really the modulus of elasticity, or it also known as the elastic modulus of the medium, while rho is just the density of this medium, of any particular medium, right, from which the sound waves are moving through. Now in gases, we have a slight modification for the case of gases. It's just that the sound waves will travel in the form of a compression wave, and gases will really have a bulk modulus of elasticity. So we'll use that bulk modulus of elasticity divided by the density of the medium or the gas, right? Now, the bulk modulus of elasticity is really defined as a ratio of stress to the volumetric strain produced by this stress. So you can also write it as, you can denote stress with sigma, and volumetric strain is really the change in volume divided by the total volume before this stress was applied. So it was Newton who proved that for the case of air, the isothermal modulus of elasticity is really the bulk modulus being equal to the stress that is applied. So this is the case where you have the isothermal modulus of elasticity. Now isothermal really means that the elasticity, excuse my spelling. Now yeah, so isothermal really means that the temperature is kept constant throughout, really. So using really this thing which Newton proved, then we can write the speed of sound as the square root of the stress that is applied to the divided by the density of the gas, right? So this is all in the case of a gas. While of course, this would also be in air, right? Because air is just a gas. Now, this isothermal propagation of sound waves in air is not really true, basically. This was what Newton assumed, and so when Newton derived this expression for the velocity, it has an error, really, and that error is of about 16% in the value of speed of sound. Now, it took Laplace to correct really the Newton's formula by saying that sound waves, they do not propagate isothermally, but they rather propagate adiabatically. Now, what does that mean? That there is no heat being transferred, right? So there is no heat transfer when sound waves propagate, right? So temperature may change, and as it turns out, really, that the speed of sound increases for an increase in temperature, and it's really something like an increase in speed of sound is of about 0.6 meters per second increase in the speed of sound, with an increase of 1 degree Celsius in temperature, right? Now, Laplace formula, the corrected formula for the velocity or the speed of sound, was given as the square root of gamma times sigma over density of the gas or any fluid. So then this term on the in the numerator, which is gamma sigma, is really defined as the bulk modulus for an adiabatic case, right? So it is the adiabatic bulk modulus or elastic modulus of the fluid. While this gamma is just a ratio of the specific heat capacity with constant pressure divided by specific heat capacity at constant volume, for the case of air, this value is really 1.42, and it's a dimensionless constant gamma.